All right, let's get started. Yeah, this is the last talk before lunch, so we'll try our best to be timely as possible. So my name is Lita Cho, and this is Tom. We both work at Lyft. I work on the service mesh and / networking team, and Tom works on the deploys team. And we're here to talk to you about our service mesh migration to Kubernetes and all the specific issues we came around. And hopefully this will give you some learnings so that when you're in your process of your migration, you could take these learnings with you. So we separated the talk into 3 parts. First is giving you context of our service discovery architecture, legacy versus Kubernetes. We'll quickly go through that so you have the context to understand the issues. And so we broke up the issues into scaling up as well as scaling down in Kubernetes. And then we are going to close it all up with future work that's still left to do. So yeah, our service discovery is fairly simple. We run Envoy as a sidecar and a bunch of virtual machines, and there's a cron job that registers IPs into a Python discovery service that's stored in Dynamo. And then Envoy pulls for that data every 30 seconds, giving the set of IP addresses it needs to start routing traffic to the services it cares about. So this is our hybrid discovery. So again, rather than Envoy sidecars polling, we've decided to send the old legacy infrastructure data. Oh, is it going? Oh, yeah. Go into the control plane. So we were migrating over to XCS control plane. And then also which is written in Go, and we are, that control plane also listens to the Kubernetes API server to get the state information of all the pods and IP addresses. And just to note that we don't use an ingress controller in our Kubernetes cluster. We use CNI, so each Envoy has a routable IP address. Each pod has a routable IP address and can talk to any parts of a VPC, similar to the earlier talk that Thomas gave today. Is basically what we use. And then the control plane then munges both data sets together and streams that out via XCS streaming and to the sidecar envoys. And this is the biggest change here. We're no longer polling anymore. We're streaming data. And this was a conscious choice so that we can resolve the service mesh as quickly as possible to get the benefits of Kubernetes quickly scaling up and quickly scaling down. And then at the end of the day, the final statement is what we want the control plane to be run in our Kubernetes cluster, and each control plane will listen to get data from the API server and split it, send that data off to the sidecar envoys. It's not clear yet whether we're going to make each cluster a separate mesh, but at the end of the day, this is kind of what we want. We want the control plane to be alongside with the pods, sending discovery data in the Kubernetes cluster. So to go into quick details, the control plane leverages the Kubernetes informers, which uses the watch API, and that's just basically syntactic sugar to handle the watch API events, parses them all nicely into nice Go structs, and we use the endpoint objects, so Kubernetes endpoint objects, which provides all the IP address for that particular service. And so it provides both old state and new state. And what we do is we just take the new state and merge that with any legacy IP addresses that are available, merge them all together and create EDS data and then send that out. The other key thing that we want to mention, which will be important later in the talk, is that we did move to streaming XCS APIs. And this is so that we can resolve the mesh as quickly as possible. The last piece of information that we need to go over is how we configured our CDS. So we both have active health checking turned on at an interval of 15 seconds. We have outlier detection enabled, so if a service or a host is sending a consecutive amount of 500s or 5xx, it'll get ejected temporarily from the service mesh. And we also have panic routing enabled, so that is turned on by default. And what that means is that if 50% of the hosts fail health checks, it will start ignoring health checking status and route traffic everywhere. So let's now dive into the issues. So we're going to first talk about scale up. So in a Kubernetes deployment, as most of you know, that there is no such thing as like a deployment. Before, in our legacy infrastructure, we would hot restart, and so the IP address sets wouldn't change very much, but that's not true in Kubernetes. Each deployment is basically a scale up and a scale down. So again, we're now propagating way more information in the mesh in time, and so let's look at each problem separately. And we kind of made this story around with the invitation to a party. So like a pod is coming in, it's like entering a party, which is the service mesh. So let's dive into scale up. So it's very important to be polite to yourself and introduce yourself to everyone at the party. So we have, during scale up, let's say a pod comes up, Kubernetes, the kubelet or the API server notices that, someone just joined the party. So someone joined the service mesh and sends an event to tell other people, or in this case, your downstream services, that a new pod has entered the mesh. And so it talks to the control plane, sends that, converts that event into EDS data, and sends that out to the downstream services. And then, again, you have to introduce yourself via health checking. So the downstream services sends out a health check, and you notify that, hey, I'm here, I'm ready to take traffic. However, so let's go back. So unfortunately, when we scaled up too quickly, we noticed panic routing would be enabled. So the intent of panic routing is to prevent thundering herd. With our legacy infrastructure, scaling up was quite expensive, so we didn't want all the healthy hosts to get overloaded. So that's the intent with panic routing. But the issue is that during a deployment, or since it's similar to a scaling up event, you can see that if more than 50% of hosts were entered, you'll unintentionally enter into panic routing. And that's because they enter in unhealthy first all at once, and then you have brief moment of panic routing, and then it will resolve itself. So working with the open source community was really great. They acknowledged this and fixed this. Snow created a PR to exclude new hosts into the load balancing calculations for panic routing. This worked both for panic routing and priority spillover. And basically you have to enable it in your CDS file, but this has solved that problem. So now if you have this configuration enabled, it won't include new hosts into the panic routing calculation. So the second issue we ran into was Envoy startup. So a lot of applications at Lyft assume that Envoy will be ready to serve traffic, and in legacy infrastructure that was true. When your deployment happened, Envoy would still be there. It was mutable infrastructure, so when it was hot restarted, Envoy will still be running. And when you scaled up in our legacy infrastructure, usually Envoy was started up first, then your application was started. But that is not true with Kubernetes. In Kubernetes, all the sidecars are started up all together. And so it could be the case where your application will be ready to run first, and then Envoy would not be there. And the one solution was to get people to change their code and handle that case. But that's not a really great experience for our product engineers, and also getting people to change code will just end up delaying our Kubernetes migration even further. So we need to come up with a different approach. So we did two things. One is we edited what readiness means for the Envoy sidecar container. So we listened to the ready admin endpoint, and what that does is it will wait until all the XCS configuration is initialized from your control plane. However, if you have initialization timeout set, it will respect that, and after a certain time, and if it hasn't initialized during that timeout, the ready endpoint will send a 200 after that timeout. So that's something to watch out for. The second thing is that we ended up forking Kubernetes so that we can implement ordering. And so through that, we ended up implementing container ordering in that fork. And it's not great that we're working with the Kubernetes community to make that better. And it seems like this is something wanted in the industry. So if you want to see what we did, you can look at our fork, and hopefully this gets resolved later on in the Kubernetes community. So in summary, for scale up, we had issues with panic routing, but due to the Upstream Envoy fix, that ended up working out properly. And then the other thing is sidecar ordering. So we added a more representative readiness check for Envoy, as well as forking Kubernetes to ensure that Envoy is started first, or all the sidecar containers are started first before the application. So great. And so Tom is now going to go over scale down.
Great. I don't think I need that mic.
Yeah, right.
Hello. OK, cool. Yeah, so thank you, Lita, for talking about scale up. So I'm going to talk about scale down. And to continue with the party analogy, it's like saying bye before you leave the party. No one likes it when you just ghost the party. Then people might say, like, where's Tom? And everyone gets confused, just like the service mesh. So let's look at what scale down looks like. So you have your pods, got some happy pods talking to upstreams and downstreams. Let's say one of the pods gets terminated and it's scaling down for whatever reason. Kubernetes will see this, send this update to the control plane, and then propagate it to the downstream. And of course, your health check will also have to fail at some point. Looks a lot like the scale-up case. So one thing we noticed when we first shipped this out was that we had this case where we would have kind of like undead hosts in local discovery. So basically, like a pod would get terminated, but then that IP address would just kind of linger in a couple hosts' local discovery. And eventually, this caused a number of issues because people just kept getting paged, basically, because the page would basically think that there were some number of hosts that were unhealthy inside the mesh, but they just weren't there, period. So something was up. The mesh wasn't converging correctly. We really had no idea what was happening, so we dug in. So the interesting thing here is that Envoy has some level of protection from like a Byzantine failure from the XDS control plane. And what I mean by that is that it kind of respects its health checks quite a bit. So if the control plane were to just like barf and tell you there's no more hosts for something, as long as the health checks are still rolling, like Envoy is going to be fine with that and just keep using those hosts. So what ends up happening is Envoy basically has to see that the health checks have failed and that the hosts are absent from a control plane EDS response to remove the host from local discovery. What we found out, though, was that there was a bug here where this had to happen in order. So with XDS streaming, this kind of made things way more complicated because basically we would kind of send the update and the entry would get stale, and we wouldn't send the update again later because XDS streaming, it's not periodic. The IP address would just kind of linger. So this is the table in which Envoy should respect as far as like health check status and discovery status. We wanted to be here. We were stuck here, and we really needed to get here to delete the thing. So we needed to fail the health check and be absent. So there's 2 patches. Thank you, Matt, for implementing both of these. The bottom one I'll talk about first, even though we kind of discovered that bug later, which is why it was later. But the bottom one is handling the health check without any regard to how the ordering works. So with that change, basically Envoy keeps track of the state of the last discovery update. And so if you start failing health checks and in the previous update you got removed, then it could clean that host out of local discovery, no problem. And then another upstream change that we made was allowing the control plane to sort of forcibly remove a host from the mesh. So this essentially allows this extra state, this draining state, for you to be able to set in XDS on a host. And so you could propagate that draining state to all the downstream pods, and they will know, like, okay, this pod is about to be deleted. I should stop routing requests to it. And once it starts failing health checks or whatever, like it's good to clean up. So yeah, so now Envoy's all good after that patch. Everything's great. It's respecting the holy table. So even after we fixed that bug, though, we started seeing still some more 503s. So we were digging into this. We could rely on retries, but we wanted to do better. We didn't want to just let this happen. So, like I said earlier, we added that draining endpoint. We wanted to take advantage of that and somehow notify the mesh that when a host is going away, start draining requests, stop sending it requests. The reason we saw this 503 issue is because we're using the Kubernetes endpoints to sort of be our source of truth as far as like what the EDS data is. And the way endpoints are handled is that they kind of get deleted like the same time the readiness check fails. It's actually concurrent. And in our case, the readiness check is the same thing as our Envoy health check. So there could be a case where basically the health check fails and then the endpoint disappears, and then it's just kind of chaos. So here's like a high-level diagram of how our control plane looks like. Like Lita was saying, we use an informer. We're using an endpoint informer. And basically, the endpoint informer takes the Kubernetes Watch API and makes it work kind of like a nice queue. The nice thing about this setup is that on the Kubernetes informer side, we're getting these endpoint updates. And you can imagine that's for like service A, service C, service D. The nice thing about endpoints is that they have the entire state of the world for that service within that cluster. So basically, the design here is really simple. You just kind of pluck this thing off the queue, and then we shove it into this cache that we have in the control plane, and then that cache gets propagated out to all the downstreams. Really simple, worked well enough, pretty easy. So again, endpoints get removed immediately once the readiness check fails. We don't have any time to send this like fancy draining update we implemented earlier. And basically what ended up happening was there's a race where the pod gets terminated, it fails health checks because it's gone outright, but this happens before the EDS removal occurs and before the active health check comes in to save the day. So this is the source of the 503s that we were hitting. So the next logical alternative is to use pods instead of Kubernetes endpoints for our control plane. It kind of makes sense. The endpoint controller inside of Kubernetes does the same thing, and we're kind of replacing endpoints with our solution, so we might as well do what they're doing. So the nice thing about pods is that when they get deleted, they have this termination grace period that you can set. And when that's set, what basically happens is the pod has this deletion timestamp field that's set at the time. It's set with the time at which the pod should be deleted. So it's a nice way of knowing that this pod is about to be terminated, and we can send a draining update for pods that we find that have that field set. The annoying thing here is that the pod updates aren't service level like endpoint updates are. We don't get the whole state of the world. We're going to get updates for every single pod, and then we're going to have to maintain a cache as well. Sounds really annoying. So if you dig a little deeper into the Kubernetes client Go code, you'll find this neat little thing called an indexer. And the indexer basically allows you to bucket the objects that you're watching in like an arbitrary way. So we have a special label on all the pods within a service, and it's really easy for us to use the indexer to just kind of bucket all those pod updates into the index by service name. So it's kind of like this extra cache, but the cache gets maintained. It's sort of like the latest state of the world for that service, or for that set of pods, rather. So what we end up doing is basically for every pod update, we just kind of pluck out the service name, put that on a queue, and then when we process that queue, we kind of take that service name out, look up that service in the index, pull out all the pods, generate a cache entry, and then put it back into our control plane cache, and then propagate that to downstream hosts. A little more complicated, but we end up getting the same benefit, which is we have the entire state of the world handled by Kubernetes, and we don't really have to muck around with our own cache. And everything's good, and we have a happy Chihuahua. So in summary, scale down, the two things we kind of had to tackle here was tackling the out-of-order bugs, notably around discovery and health check data, and then also getting our control plane to monitor pods rather than endpoints, because that seems to give us time to send the draining update, and it allows us to avoid, just sending the draining update, basically. So everything's good. We got all these cool check marks. So in summary, everybody likes talking about paradigm shifts, so I will talk about the paradigm shift as well, where the changes essentially are moving from node level changes, like Lita was saying earlier, in our VM infrastructure. The VMs would kind of stay where they were, and we would kind of update things in place. But we're sort of moving those levels of changes with Kubernetes into the network topology or the network topography. And so that's to take advantage of Kubernetes' quick scale up and scale down. And again, few things needed tweaking to get there. We had to patch Kubernetes, which was not ideal, but that's what we did. And yeah. And as far as future work goes, Thomas from Cilium had a very interesting talk about running Envoy as a daemon set. We run Envoy as a sidecar on every pod, and this is expensive for compute reasons. It also, makes mesh scaling more difficult if you have even more envoys to deal with. Seems interesting, seems complicated. It's probably something that we'll dig into later. The other thing that we're looking into is that we have this one giant mesh, or essentially two giant meshes, one for staging, one for production. And it's hard to propagate that information in time across to all the downstream hosts when things are changing, especially when things are rapidly changing in Kubernetes. So we're looking into a couple strategies, one of which is cutting up that mesh, maybe cutting them up by AWS availability zone or by cluster. And another is batching the updates, so that in case there is some big scaling up or scaling down event, we can just batch those updates and send one update instead of sending 1,000 or however many we have to. And we're really interested in some of the Envoy OSS changes with federation and supporting multiple control planes. So thank you. And now we have an invitation to a party for you, and hopefully you say hi and bye to us appropriately. Please join us at the Lyft Happy Hour on Tuesday, November 19th, at a bar called Thorn Barrio Logan, which also sounds like an auto-generated password. Please RSVP on the website, or you could just show up at the door and you'll be fine. Yeah, thank you.